this next topic is something that we actually didn't touch on so much in the Sunday sessions, but I thought it would be worthwhile because I think this is a fairly easy question to ask on an interview. And the question might not just be, here's a structure, tell me how big it is. But as you're producing some sort of a structure, it isn't unreasonable for the interviewer for you to ask you how big would this structure you just created be. So let me pose this question to everyone here. If I called size of struct X, what would this return? Anyone have any thoughts?
Isn't it six bytes? Because the last element, it's basically, so first of all, size of is an operator that is calculated during compile time. And during compile time, we have no idea what the last element in the structure is. So we can assume that it is 0 and then come up with 6 bytes for the whole structure.
Yeah, you're definitely on the right track, and I like the way that you're thinking. Size of is going to be determined effectively at compile time, and this final field in this structure doesn't have any size associated with it.
I think I have to rephrase it. I think the last one would be considered as a pointer, and pointer on a 64-bit architecture is going to be 4 bytes. So the total is going to be 10 bytes.
So not to be nitpicky or shoot you down, I appreciate you going out on a limb and speaking up here. But I wanted to correct a couple things. First is on a 64-bit machine, a pointer would be 8 bytes rather than 4 bytes. But that's not necessarily here nor there. But I think you were correct on the first thing that you said. In the context of a structure in C, this is called a flexible array member, and this field doesn't have any size. It's not a pointer. This will actually, or at least potentially, be used as an array in kind of a regular array semantics. But there's no size associated with this. There's no memory inherently allocated on behalf of this. Sometimes you might see this written as C0, but this when it's empty on the inside specifically is where we have the C, not C++, the C flexible array member. So back to your other point, you give a couple of different aspects to your question. I want to make sure I touch on all of them. Your initial response was that this last one doesn't have any size, so field C essentially adds 0 bytes to the total size of the structure. So then the size of the structure is going to be determined by these first two, fields A and B. And if you remember from this past Sunday, we said that assuming it's not a packed structure, structures will be aligned by the compiler on your behalf according to the architecture it's being built against. And in most architectures, 32-bit or 4-byte fields need to be aligned to a 4-byte address, and a 2-byte field needs to be aligned to a 2-byte address. So let's just diagram it out over here. Let's say here's our beginning. Let's just call it address 0. What we would see in memory is A being a 4-byte field taking up those first 4 bytes, and then B subsequently taking up these subsequent 2 bytes. And when we talked about alignment and padding, we talked about 2 different types of padding. Either the padding that is needed between 2 bytes, or padding that's needed at the end of the structure. In this particular case, no padding is needed between the 2 bytes. A is able, just being inherently the very first field in the structure, is able to be aligned to 0, a multiple of 4, if you will. And then field B, being a 2-byte structure, is able to also start off at address 4. So there doesn't need to be any padding between A and B. However, we do need to have padding after B in order to make the next entry of A line up correctly. Because remember, if we have this struct X in an array, what we'd end up seeing in memory is A, B once again. There's this subsequent entry A needs to be 4-byte aligned. This is what it would look like if we had something, for example, like struct X. We had some array of length 2. This is what we would have in memory. So this second entry of A's needs to be 4-byte aligned. Therefore, we need to make sure we add 2 bytes of padding here, well, and similarly 2 bytes of padding here to make sure that it lines up correctly. So because of that, the size of the structure ends up being 8 bytes. Once again, one set of bytes, the next 4 bytes. And this field C in this particular example is essentially can be ignored. Any questions so far about this alignment and how it impacts the structure size? Okay, so this is mostly the stuff that we were talking about on Sunday, although obviously this is a different example, but hopefully we're not necessarily introducing anything too new here. However,
just a quick question. So here it is mentioned as UNT64, right? So isn't it, shouldn't we assume that it's a 64-bit architecture instead of 32-bit?
You can have a 64-bit field on a 32-bit architecture. So the simple existence of a 64-bit field that probably doesn't imply anything regarding the architecture it's running on. But even if this was a 64-bit architecture, my expectation would be that it would still have size 8 bytes, because a 32-bit field is 4 bytes regardless of the architecture, and a 16-bit field is 2 bytes regardless of the architecture. And the alignment requires of those two fields. Once again, I'm somewhat generalizing for like a regular system. Obviously, you can design a system that has weird or different alignment requirements. But for a regular system, these fields A and B would continue to have these same alignment requirements. And my strong expectation is that if you code size of on this structure on a 32-bit or a 64-bit machine, you should get 8 bytes in either case.
Yeah, I agree with 8 bytes. That is not a problem. Yeah, I was just curious if something else comes up and if there is UNT64, we still stick to the 32-bit.
Yeah, there's a reason why I put that UNT64 there. I want to approach that here on this next slide. This is part of the point I'm trying to make. Here's a very similar but slightly different structure. Here I have a 16-bit field, a 16-bit field, and a 64-bit field. And I could similarly ask you, if I called size of this struct Y, what would it return? And we can do the exact, oh, sorry, go ahead.
No, sorry, I preempted. I was just saying it's going to be 8 byte. I had some question on the previous one, but that's fine. I think we'll go ahead. Sorry, Ham.
Oh, no worries. 8 bytes is actually a very interesting prediction, and let's get to that in just a second. So let's do the same sort of memory map as we did previously. We're going to have A and A, 2 bytes, 2 byte alignment, perfect. We're going to have B and B, also on a 2 byte alignment. So everything's fine and dandy so far. So if we simply went off of that previous example where we only looked at fields A and B and ignored C, one might think incorrectly that this would have size 4. But that would be incorrect. I forget who it was, but your response was exactly right, that this is going to have size 8 bytes. Can anyone tell me, or maybe if you want to speak up again, why is it 8 bytes? Where is that extra 4 bytes magically coming from?
Yeah, I think it's the same principle, right? That if you have an array of this structure, the second element in the array should be aligned to the 64-bit boundary here, because that's the last element here, right? So in the structure.
Well, let's go back to this previous example. here we had a 64-bit. Well, I guess your argument of 8 bytes is still the case. But your argument here is that we just got lucky in terms of the 64-bit alignment of C. That's correct?
No, in this case, I think the padding would be only 2 bytes required, because the C would fall to the 64-bit address boundary. I mean, in the first case.
Cool. Well,
Case,
I like your explanation. I think maybe I'll for those that are following along as well. Maybe I'll say it from a slightly different perspective. Let's approach this question not necessarily from an alignment question, but let's maybe approach it from a semantics sort of question. If I wanted to use this structure in practice, what I would likely need to do is not only have memory instantiated for me for A and B, I also presumably want to allocate some memory for C. So a common.
I had that question, like, because if you are going to do that, you will never have a case of Y being a array of structures, right? So
exactly.
Anyway.
I would need to double check, but I actually think that having an array of Y might be illegal. I'm not sure that it's legal C to have an array of struct Y now that we have a flexible member in it.
Right.
Prabhu, do you not Prabhu, sorry, Raghu, do you remember offhand if that would be illegal?
Yes, you're right. Since the size of the array element here is undetermined, it's not possible to have another aggregate structure which includes this as a base type.
Perfect. Right? Awesome. So we cannot have an array of struct Y anymore because we have this field C within it. So back to my kind of alternative perspective on how we determine how big is this structure if we called size of the structure. So oftentimes you might end up using a structure or allocating memory for it, something along these lines. You might call malloc, you might call size of struct Y, and then what we're going to have is size of uint64t times however many entries of C that we want. Let's say 5. So this is the line of code you would use in order to allocate memory for this structure. In this case, I would have allocated memory for fields A and B and allocated memory such that field C is an array of 5 64-bit integers. But now we need to make the math work. We said this is the end point. Let's work our way back. If we're going to use this in order to allocate memory and figure out how much memory to allocate, we now need to figure out, okay, what is the size of Y that makes this whole equation work out correctly? So A and B we talked about up here would be placed in a line along these lines here. But where does C need to start? C needs to start on a 64-bit boundary, being a 64-bit field. This next line here is not a 64-bit aligned memory location. It's a 4-byte aligned memory location, but not an 8-byte aligned memory location, which means that in this structure, if C is going to be present, C would need to start down here. These would need to be padding, and then C would need to consume those next 8 bytes. And obviously, if we had an array, C would continue further down as well. So C needs to start here at offset 8. A and B are fine where they're at. So in order to make this math work out, if I say size of uint64 is 8 times 5, so I got 40 down here, and I have size of Y, and if I only had a size of Y of 4, 4 plus 40 isn't actually enough memory to store the structure I want, given this padding that is added, that is necessary here. So the only solution to that problem is that size of struct Y needs to incorporate this padding as part of its size. So size of Y here is actually going to be 8 bytes. Not because A and B together consume 8 bytes, but because C, if and when it's present, needs to be 8-byte aligned. We need to make sure that everything up until C consumes some multiple of 8 in terms of its memory consumption. The reason why I brought this up is we talked before about how sometimes you need to have padding between fields and sometimes you need to have padding after the final field in order to make the alignment work correctly if it was used in an array. This is kind of a special case where we need to have extra padding added kind of at the end of the structure, but not because struct Y is going to be within an array, but because of this flexible array member here at the end. So earlier I said, oh, we ignored the fact that the field C was present when it came to us calculating the size of the structure, but we actually can't ignore C. We need to consider C from the perspective of padding required when we're determining how big the structure is going to be when you call size of it. And as I premised all of this, I don't normally see someone just giving you a structure and asking you how big it is. It's not something that, not that it couldn't be done, but I don't usually see that as a prompt oftentimes in the interviews. But what I do see quite often is someone asking you to, let's say, implement malloc or implement this callback structure or implement some sort of bigger design. And as part of that design, you need to design your own data structures. And hopefully your data structures are inherently concise and compact and aren't wasteful of memory. But regardless of whether they are or not optimally sized, it is a very easy question for an interviewer to ask, oh, how big would this structure be? How much memory is this going to consume both individually or maybe in aggregate if you had multiple instantiations of this structure in your code? Okay.
Can I ask a question?
Absolutely.
Yeah, so I was just wondering the use cases. I mean, I've seen some use cases, but about this, like the last element being empty, and then you over-allocate the memory, and then you can access that particular element via in this example, like C C is as an array member. As a structure member. What would be some? I mean, from your experience,
I see this come up a lot in all sorts of areas. Just the other day, yesterday, in fact, I saw this come up with regards to hit events. So let's say a hit event is like a mouse move. So our hit event is going to have some header fields. It's going to have a report ID. It might have a timestamp. It might have some other sort of metadata like that within the header. And then there's going to be some, let's call it device specific data. In the case of a keyboard press, it might be literally an int representing which key. Maybe it's an accelerometer sample, in which case there's an X, Y, and Z field. But whatever it happens to, oops.
I think there's some issue with the.
Yeah, thank you. It's got very zoomed in.
Yes.
Oh, there we
Maybe.
go. Cool. Sorry about that. This is one of the issues. I'm doing all the writing on an iPad, but I'm sharing a desktop screen, and every once in a while the resolutions of those things don't match up. So sorry about that. Thanks for pointing that out. So we have some common metadata, some common header fields, and then some device specific content. But we want some way of representing this generically in code. So we might have a structure that is an int report ID, a 64-bit int timestamp, and then we have, let me do a little bit differently. Then we have a simple byte array for the payload. Where whatever that specific device-specific information happens to be can live there. This payload is going to vary from device to device. In some cases, it might be 3 integers in the case of that accelerometer sample. It might be just 1 integer in the case of a mouse or a keyboard move. Maybe there's, in a keyboard, there might be multiple data fields involved with regards to whether or not there was multiple presses or how long it was pressed, in addition to what key was actually pressed. So you have all that kind of payload information that is different from device to device or from event to event, but we need one common structure to define it all. So this payload ends up being a arbitrary or flexible length array member. And then when you actually need to use something with that payload, what you might have, let's say this is struct Y once again, we might instantiate struct Y, let's call it lowercase y. Y has some sort of payload, and then we have our, let's call it our keyboard event. That's the name of some other structure that has our keyboard specific fields within it. Let's say this, probably go like this, equals y dot payload. And now we can go on using our new keyboard temporary variable and access the key pressed or whatever those fields happen to be within that payload. Did that example make sense?
Yeah. I mean, the other way to look at this is like payload could be a union as well, right? And then you have different payload types can be members of that.
Absolutely. If you knew in advance all of the different type of, and this, let's say, take this example, hit event. If you knew all the possible different hit events that could occur in the system, you could instead replace payload with a union of all those possibilities and then access it as a union. But in this particular case, we don't have a complete list. That list changes, or there might be some custom hardware that has its own unique data type that the architecture itself doesn't know. That's one of the other beauties of this, is that the payload can be passed along opaquely from the perspective of the framework, but the fields, which might be necessary to the framework, are accessible to it. So yeah. I see this pattern being used all the time for frameworks that are responsible for storing, communicating, passing along data that it doesn't need to know, doesn't need to understand, but someone else down the line does. One other case where I see this sort of thing being used is for messaging, like communication messaging, nesting structures. You might have, for example, several layers of headers wrapping around some data. You can look at like the internet, the IP sort of case where you have IP packets, TCP header, an Ethernet header. All of these things might be, in a, logically speaking, prepended to the data itself. And you could potentially have your topmost structure have whatever sort of metadata header, whatever sort of metadata header fields you need, and then you have the payload, which is once again our flexible array member. And then we have some other structure that represents our middle layer, our middle header, that similarly has some header fields and a payload. And we can go on down the line. I've actually implemented myself cases where we had 3 or 4 layers of nested flexible array members because we had multiple headers that we wanted to pop on or off the data at different points in our framework, in our stack.
So in those cases, do you serialize the payload individually as a separate function that goes into the payload, like the next layer? or do you?
I've done it in both. Well, what do you mean? Serialization is kind of a loaded term. What do you mean?
Well, I mean, like you can't just do necessarily. You can't rely on a mem copy directly from structure to payload of the next layer, right?
In some cases you can, in some cases you can't. The issue
Right.
with well, memcopy is actually less. Memcopy actually solves most of your problems. The previous example I had where we're literally using the address of that location to access it. The issue we have then is that the alignment required by this structure might not be coincidentally what the alignment is within this payload. So doing this and accessing it directly does have alignment concerns such that it might not always work. But the moment you start mem copying it, you can mem copy the data out of the payload into some other structure that is appropriately memory aligned and kind of solve that problem. But to answer your question, I've seen both. I've seen cases where it's done like this, where it's accessed directly, and we've just been very careful to make sure that the alignment is correct. I've seen cases where mem copy is used, and I've also seen cases where the format, the encoding of the data within our flexible array member is completely independent from the formatting of the rest of the structure. For example, this payload might actually be an XML or JSON or protocol buffer. It might be a completely independent way of formulating the data. And so this happens, these top two fields are still in a C structure format, but the payload is in a completely different serialized format for whatever sort of reason it happens to be that way. And those are all valid use cases, all realistic use cases, and frankly, all things that might come up in an interview. It wouldn't surprise me for someone to give you something like this and expect you to be able to use it because it comes up fairly common in an embedded sort of environment in terms of design work and implementation in the first place. Yeah, I'll leave it at that.
Great example, Glenn. Especially, the fact that the last field can be of any format. So that means the initial fields must identify what that format would be, so that it can be properly interpreted, right?
Exactly. Yeah. So oftentimes you might see in this sort of thing, I mentioned before report ID, or you might also call it something like an event ID or something that uniquely identifies how the payload is encoded such that you know how to interpret it someplace down the road. You also would oftentimes see a length field because this structure, right, this field in the structure itself doesn't actually tell you how long it is. So depending on how your system is designed, you might need to have an explicit field in your structure that states either how many bytes or how many array entries this flexible array member consumes.
Thank you.
Glenn, can I have a question? Okay. So I understand this slide that to use this field, when we allocate this data structure, we need to malloc past the end, right? So that this C points to this allocation.
Yes.
But can you go to another slide? The one that you had like a use case. Yes.
Sorry, this is my problem. When I start writing over the slide, it gets more chicken scratchy. But yes, go ahead.
Okay, so can you explain me? So you declared data structure type Y and variable is Y.
Yep.
And okay, so what is the next line? Can you explain me this next line?
Sure. So here is my actual memory. This isn't the pointer. This is actual memory. And I guess how about this example actually might be a little bit misleading in terms of what I want to say next. We can actually, if you don't mind, let me change this a little bit to kind of answer your question better. And let's say that this was something malloc or given to us, this memory was already in use someplace else.
Okay, okay. Now I understand. It makes sense now. Okay, but yeah, just finish your explanation because but I think I understand. Okay, just finish.
Yeah. Yeah,
Or
the code I had originally would still actually be legal code. The compiler probably wouldn't complain about it, but it wouldn't. Those two lines wouldn't have been useful in and of themselves.